All right, now we're live, so anything you say is going to be posted to YouTube. Um, our first speaker of the day is Elia Gorokhovsky
From Harvard.
from Harvard. I was going to talk about Tauberian theorems. Take it away.
Thanks for the introduction. I think let's start this off with something very accessible. I'm going to point out some references for now. So the main reference for this talk is an expository article that came out last year by Elia Pierce, Carolyn Burnage, Lunko, and also Simon, which is called Introduction to Tauberian Theorems for Arithmetic Applications. And although I won't be using this reference very much, I really wanted to shout out an article by Brendan Alberts called Explicit Analytic Continuation of Euler Products. Which, even though it doesn't contain any Tauberian theorems, is very useful for applying them. So this talk is about number theory. And in number theory, we often study sequences of arithmetic interest. Of numbers, which for the rest of the talk, I'm going to assume are non-negative. So for a totally arbitrary example, one might consider counting number fields of fixed discriminant. And usually these sequences are pretty hard to understand, but as arithmetic statisticians, one thing that we might want to know about them is some aggregate information, like counts or averages. So if your sequence is Galois G extensions of fixed discriminant, then the partial sums of this sequence would be G extensions of discriminant bounded above. And the way we do this in analytic number theory is by going through analysis. So part of the goal of this talk is to show you how these arithmetic information interplays with the analytic information that we're about to see. So given a sequence of arithmetic interest, one can construct an object in complex analysis called a Dirichlet series. Which I will denote by A of S, and is a sum from 1 to infinity of A sub n, or sequence times n to the minus s. So for the rest of this talk, I'll fix this notation A of S and A sub n. And the way we go from complex analysis back into number theory to get these aggregates is what are called Tauberian theorems. So in the rest of this talk, I'll give two Tauberian theorems, one of which is kind of minimal in the assumptions we make on analytic properties of the Dirichlet series, and the other which assumes a little more about the analytic properties and gives you a little more about the arithmetic properties. And interspersed with those, I'll give some examples of Dirichlet series and how we can use Tauberian theorems to compute their partial sums. So first, I want to point out some of the main players in the world of Dirichlet series. The Riemann zeta function, which is associated to the sequence s of n equals 1, and so is written by this has some nice properties. For example, it has a meromorphic continuation to the whole complex plane, which has only one singularity, which is simple at s equals 1 and has a residue 1. And it also highlights something that's very nice about Dirichlet series, which is that they can be used to view these sequences of arithmetic interest in a local sense. So it has what's called an Euler product representation. Which is a product over all primes of something called Euler factors. So in the case of the zeta function, the Euler factors are geometric series in the prime. And this basically encodes the idea that each natural number can have any power of any given prime dividing it. And just to give one more example of an Euler product that I'll be using later, we might consider counting square free integers. So to build a Dirichlet series out of this, we can start with an Euler product. The nice thing about being square free is it's entirely determined by local information, which is that for any prime, it cannot be divisible by the square of that prime. So the Euler factor will just have one term in it with a key. And if you look closely, you can see that this is related to the zeta function in a nice way. So the power of this representation is that if you know something about the analytic properties of the zeta function, then you also know something about the analytic properties of this Dirichlet series, namely where its poles and zeros are and what the residues are. And because of this, I will be able to do the rest of this talk without invoking any other analytic properties of Dirichlet series other than the zeta function. So now I will state the first Tauberian theorem of this talk, which is due in some part to Ikehara and Wiener. And more generally, to Delage. This in the 30s and this in the 50s, 19. So the general idea is that if you have a Dirichlet series, it will be defined on some half plane in C, and it will have some pole, which is the rightmost of all of its poles. And on this region to the left of the pole, sorry, to the right of the pole, it will be analytic, and to the left of the pole, we don't really know anything. So we'll get some kind of representation for the partial sums of our sequence, which will be determined by the location of the pole, the order of the pole, and also by the residue of the pole. And if we can push a little further, if we know something about the properties of the Dirichlet series to the left of this pole, then we can get a little better error bounds. So this is going to be a minimalist theorem. I will assume as little as possible, and then I will explain to you why this really is as little as possible. So I want to assume that A of S, my Dirichlet series, has a meromorphic continuation to the half plane real part of S greater than or equal to alpha for some alpha bigger than 0. And also that in this domain, A of S has only one pole, which will be at S equals alpha on the real line of order M. So this assumption is crucial, and you'll see why later. The conclusion of this theorem is we obtain an asymptotic for the partial sums. Which is a constant times some power of x times some power of log x with a kind of uninformative error term. So one of the great things about Tauberian theorems is you can kind of guess precisely what the rate of growth and leading coefficient of this partial sum is, even if you don't know precisely how to prove the analysis. So if you can make some guesses about the analytic properties, we'll figure out something about what we should guess about the behavior of this sum. And in fact, we also have a precise formula for the leading constant. So the leading constant C is defined as follows. If I write my Dirichlet series as some holomorphic function divided by S minus alpha to the M, plus some other holomorphic function where I assume that G of alpha is not 0, then the constant C is just G of alpha divided by alpha times M minus 1 factorial, which looks suspiciously like a residue, and we'll see why a little bit later. So I want to give some examples of applying this theorem with my favorite Dirichlet series. The zeta function. So in this case, we know the order, location, and residue of the pole. The location of the pole is 1. The order of the pole is 1. And you'll notice that if M equals 1, then this leading constant is just And if m equals 1 and alpha equals 1, then this leading constant will be precisely the residue of A of S at 1, which we know is 1. And so we obtain the celebrated result that the sum of all the 1s from 1 to x was x plus little o of x, which is very useful. I want to give another example, which is a little less trivial. So in this case, the Dirichlet series would be the series whose coefficients are the indicators for square free integers. So we want to understand where the zeros and poles of this are, and these basically come from understanding the zeta function. And so we know it definitely has a pole at s equals 1 of order 1, and residue 1 over zeta of 2, which is 6 over pi squared. But we needed to have no more poles in this half plane, but under some mild assumptions, this is true. Then we obtain an asymptotic for the number of square free numbers less than or equal to x, which is 6 over pi squared. So I want to point out that you can actually prove this with the power saving error term without assuming the Riemann hypothesis. And this is the correct answer. But I think the great thing about this is that we didn't actually do any number theory. We just plugged the zeta function into this Tauberian theorem. And even though we got a weaker result, we got a good guess for what the order of growth and the leading constant were. So maybe in the next talk, we'll see that if we make some guesses about how the Dirichlet series behave, we can get precise guesses about the number theory, even if we don't actually know how to prove them. And the last example I'll give in this vein is to convince you that this assumption that I just erased, that there's only one pole in the region, is absolutely necessary. So I'll give a very simple Dirichlet series whose only crime is to have more than one pole on the line real part of s equals 1. So this is just a sum of 3 copies of the zeta function with some linear coefficients and some shifts. And if you write out the Dirichlet series representation of this, what you'll get is a 1 from the zeta function plus cosine of log x from the vertical shifts of these 2 copies of the zeta function. So it's because n to the I is e to the I log x, and then you can express the cosine in terms of these. So this is a fairly well-behaved sequence.
Actually, X.
Sorry?
X is something else.
Yes, sorry. And fairly well-behaved sequence, except that it has this oscillatory behavior, which we'll see is kind of a problem, because in the conclusion of the theorem that I didn't erase, in the conclusion of the theorem, we want some kind of well-defined order of growth, and we'll see that this thing has some oscillation in the partial sums, which prevent us from getting anything that looks like this. So indeed, partial sum of the sequence looks like x plus sum of cosine of log n. And if you want to check, you can approximate this by an integral. And do this integration by parts twice to obtain x over the square root of 2 cosine of log x minus pi over 4, which definitely precludes us from having some well-defined monotonic leading term. So even though all we did was introduce a couple extra poles on this vertical line, it automatically breaks the conclusion. And so you can see that this assumption is absolutely necessary. And now we'll see that if you make some more assumptions, you can get a little better of a result. So the idea here is we'll still have a pole at s equals alpha, but maybe we can meromorphically extend our Dirichlet series a little bit further to the left. Then instead of just having a little o of x to the alpha log x to the minus 1, which is the worst possible error term, we will instead have a power saving. And the power that's saved is going to depend on how much we can continue our sequence series to the left. So now I will assume that A of S has a meromorphic continuation to a slightly bigger half plane. Real part of S is bigger than or equal to alpha minus delta for some delta between 0 and alpha. And once again, we're going to assume a single pole. At the same place. And I will make one more assumption, which is kind of important, on the growth of this function. So the assumption that I'm going to make is that my Dirichlet series grows at most polynomially on the vertical line, which is the leftmost line in the domain of meromorphicity, in terms of the imaginary part of the argument. And I'll also add a little log factor for aesthetic reasons. So the reason I want this first condition will become apparent soon. So let me go over the proof.
Is just any.
Yeah, kappa is.
Okay.
Let's just say non-negative integer.
Yeah.
Actually, let's just say non-negative real number. Does not need to be an integer, and in fact, usually will not be. Then the conclusion we can draw about the partial sums of the sequence is we have some main term, which I will write explicitly as a residue. And we have a power saving error term, which is x to the alpha minus delta over kappa plus 1 log x to the m minus 1 if kappa is positive. And unfortunately a little messy, but x to the alpha minus delta times log x to the m if kappa is 0. So if kappa is 0, you pick up a small little extra log term. But other than that, so we get a nice power saving, and basically it depends on both how far you can push this contour to the left and also how fast the Dirichlet series grows along this vertical line. And I also want to point out here, the main term looks a little different, but it is essentially the same. So if we actually try to compute this residue, it will be 1 over m minus 1 factorial limit as s goes to alpha of some m minus first derivative of s minus alpha to the m, a of s, x to the s over s. And if we once again write a of s in terms of these holomorphic functions, then this term will become g of s plus s minus alpha to the m h of s. And if you work this out, what happens is, because we're taking derivatives, we have to do some product rule nonsense. And every time we take the product rule, we can choose which of the two parts of this product to differentiate. And the part that we differentiate that gives us the biggest growth in x is this x to the s term. Every time we differentiate, we'll pick up a log x. And so when we differentiate m to the m minus 1 times, we pick up log x to the m minus 1, and then some lower order terms. And then once we do that and just evaluate at alpha, then we'll actually get the same leading term and a few terms that are lower order in log x that previously we could have just absorbed into the error term. So really the main term is the same up to a leading order in log x. And in fact, you get a little more precise thing, which is x to the alpha times some polynomial in log of x. I'm just going to rewrite everything over here so I can use that side of the board. And I'll give some indications of the proof. This is going to be a pretty standard argument, which relies on Millin inversion. And I just want to go through it to explain why pushing the domain of analyticity of the Dirichlet series gives you a little better error bound. But I won't give too much detail. So most of the difficult part of this proof comes in the following step, which I'll call smoothing. So instead of considering some partial sum, which I'm going to instead think of an infinite sum with an indicator function attached. I'm going to consider the same sum, but with the indicator function replaced by a smoother function which is an approximator to the indicator function. So the reason I want the smoother function, which will come up in a second, is that we're going to be taking some kind of integral transform of this thing. And the smoother it is, the faster the integral transform will decay. And if we get fast decay, then we can get small error terms. Because this thing is not very smooth, so the integral transform does not have fast decay, and we get big error terms. So the hard part of this proof is really to choose the smoothing function, which is smooth enough, but also approximates this well enough that we get small error terms. And everything else will be fairly standard. But I won't talk about how to choose the smoothing function because these are just indications of a proof. So step 2 is Mellin inversion. And I'm just going to use something called Perron's formula here for the smooth function phi. So the formula says that my smooth sum is equal to some integral over a vertical line in terms of the Dirichlet series and a function phi hat of s, which is called the Mellin transform of phi. This Mellin transform is defined by integral of phi times phi of u times u to the s minus 1 du from 0 to infinity. And I'll do this integral over a vertical line, which is to the right of my singularity. So if you look closely at this Mellin transform, you'll see that if phi is differentiable, we can integrate by parts to move a derivative from here to here, which will integrate the u to the s minus 1 term and thus obtain an s in the denominator. So every time you differentiate phi, you can add a decay by a factor of s to this Mellin transform. And the more times phi is differentiable, the faster this thing decays. And the faster this thing decays, because we have a growth condition on the Dirichlet series, the better we can bound this integral. So step 3 is going to be actually computing the integral. So, draw a picture of what's going on here. We have a pole at s equals alpha, and we have a domain of meromorphicity, which is a little further to the left than that. And we want to compute an integral along a vertical line, which is to the right of the pole at real part of s equals sigma. And so the way we're going to do this is by integrating over a rectangular contour, which passes to the left of the pole. And by the residue theorem, this will be expressed in terms of the residue at the pole alpha of the integrand plus some other integral terms, which I'm going to name after parts of this contour. So I'll call the other vertical parts 2 and the horizontal parts 3 and 4. So there will be 3 integrals involved in this rectangular contour. What I mean to say is that we're actually taking a principal value of this integral, so we should integrate from minus it to it of some positive number t, and then take this t to infinity. And then ideally what will happen is that some of these integrals will be very small, and the residue will dominate, and this will become the main term. So the final step is bounding the other integrals. And this is where the growth condition really comes in. So because we have a growth condition on the Dirichlet series A of S on these vertical lines, so we have a growth condition on the vertical line which is to the left of the pole, and we can use the Fragment Lindelof convexity principle to transform this into a growth condition on the entire vertical strip on which this function is defined. Between alpha minus delta and the rightmost boundary sigma. And using this, the integrals 3 and 4 will just go to 0 as t goes to infinity. And the integral 2 will contribute to the error term. So that's all I want to say about this group for now. And for the remainder of this talk, I'll be giving an extended example, which goes from the bottom to the top of the stack of things that you do to get from arithmetic questions to analytic questions back to arithmetic questions using a Tauberian theorem. So what I want to do is I want to take partial sums of the sequence of square free numbers. But instead of just taking a square free number, I'm going to assign weights to them. And the weight is going to be 2 to the power of the number of prime divisors. So for example, I'll give 2 a weight of 2 and 6 a weight of 4. Okay, so how do we go about computing a Dirichlet series for this sequence? Well, one way to do this is to try to get an Euler product for it. So in the case of square free numbers, just the indicator function, the Euler product looks like product of real primes of 1 plus p to the minus s. But because I'm counting with a weight, I just want adding an extra prime to the factorization to incur a cost of a factor of 2. So the Euler product representation of this Dirichlet series will look like this. And so in order to check where this thing converges, we can take the log. And it works out to be roughly the sum over all primes of 2p to the minus s, which converges absolutely when the real part of s is bigger than 1. So one might expect this thing to have a pole at 1, and then the order of growth, at least in x, will be 1. Now, in order to apply any Tauberian theorem, whether it's the first theorem or the second theorem that I stated, we're going to need some kind of meromorphic continuation of this, at least to a vertical line. So let's try to continue it. Now, unfortunately, I don't know anything about any Dirichlet series other than the Riemann zeta function. So the only thing I can try to do with this is to relate it to the zeta function. And the way I'm going to do that is by looking at the individual Euler factors. So the main obstruction to converging left of real part of s equals 1 is this p to the minus s term, because the sum of the reciprocals of the primes diverges. And so in order to make this converge a little further to the left of that, I want to cancel out this p to the minus s term somehow. And I'm going to do that by multiplying by Euler factors from the zeta function. In order to cancel out 2p to the minus s, I want to multiply by the square of 1 minus p to the minus s. So this thing will be something like 1 minus 2p to the minus s plus some other things. And then when I multiply these things together, this and this will cancel, and I'll end up with only higher powers of p to the minus s. In fact, what you get is 1 plus 1 minus 3p to the minus 2s plus 2p to the minus 3s. And the conclusion we draw about the Dirichlet series is that our series A of s is equal to theta of s squared times the product. Another Euler product, 1 minus 3p to the minus 2s plus 2p to the minus 3s. So I'm going to call this other Euler product h of s. So h of s will be 1 minus 3p to the negative 2s plus 2p to the minus 3s. And if we take the log of this is roughly sum of the primes of minus 3p to the minus 2s plus 2p to the minus 3s. And this converges absolutely for real part of s bigger than 1/2. So by taking out factors of the Riemann zeta function, we've managed to parlay the domain of normorphisticity of this a little further to the left from real part of s greater than 1 to real part of s greater than 1/2. So here's the pole at s equals 1. Also from this representation, we get that it's a pole of order 2, and the residue at this pole will be h of 1. And here at real part of s equals 1/2, we have the line to which we can continue this. Now this information is obsolete, so I can erase it. And so we have information about the pole, which is that it's located at alpha equals 1, and the order of this pole is m equals 2. And the last thing we need, which is vitally important, is this growth condition. Thankfully, we can determine it from a growth condition on the Riemann zeta function using standard convexity balance. So this thing is bounded above roughly by some constant times a polynomial in the imaginary part of S, which is given by delta plus epsilon on the vertical line, real part of S equals alpha minus delta, where epsilon is an arbitrary small positive constant. And the last thing we need to do to apply this Tauberian theorem is to compute the main term. Which is the residue of this function a of s times x to the s over s at alpha. And so I'll briefly do a residue computation here. But to spare you the details, what you end up with is h of 1 times x log x plus h prime of 1 minus h of 1 x, I think. So this will be the main term. And the error term is going to be power saving, and it's going to depend on this delta. So we might as well push the delta as far left as we can, but we only got a continuation to real part of s strictly greater than 1/2. So we can't make delta equal to exactly 1/2, which is what we would ideally want, but we can at least bound this above. So this growth condition is satisfied with kappa equals 1/2, for example. And we're going to have it. And delta is just going to be some slightly less than 1/2. And so the error term we end up with is big O of x to the alpha minus delta over kappa plus 1, which will be big O of x minus to the 1 minus times some log factors. One minus 1/2 over 3/2 plus epsilon, which is 2/3. So as a result of this, we get a asymptotic for a weighted count of square free integers. Which looks like some Euler product leading constant times x times log x plus another thing times x plus this error term. And in general, if you work with these kinds of theorems, you should expect that your main term will look like some power of x, some power of log x, possibly an Euler product leading coefficient, and hopefully a power saving error term. And that's all I have to say.
Right.
Sorry?
In your sum, what should be AN?
I wrote square free under the sum.
But you want the.
Yes, but it should be 2 to the. Thank you for the catch. And that's all I have to say.
So with this growth condition, you said that's just like something literature that I want to find about this. Where was that justified?
About the zeta function?
Well, for AS.
Yeah. Okay, so for the zeta function, the way that you can do this is so first of all, AS is described as zeta squared times some Dirichlet series, which will converge absolutely on real part of s greater than 1/2.
Oh, so all you need is for say.
Yeah. So this thing is going to be uniformly bounded. And the zeta function you can get by bounding it beyond 1 with the same idea, and beyond 0 with the reflection principle, and then between 0 and 1 using the Lindau fragment Lindau convexity. Questions?
I do in this case, is there much you can say about H of 1 is just something very
Yeah, I didn't work it out, but you can just compute it probably. It's this explicit Euler product where you plug in 1 for s, so Yeah. If you'd like, I could compute it and send it to you at some point.
Yeah. All right. Thank you.
The coffee break is gonna be around, they're setting it up, so maybe